All of this is what it takes to perform conducted emissions testing to the automotive standard CISPR 25 on a lab bench. I'll walk you through every part of a mostly standard compliant voltage method test setup, run a real pre-compliance measurement, and highlight a critical limitation that can easily invalidate your results if you're not careful. I use a 100 by 40 cm galvanized steel ground plane, 2 mm thick, mounted at bench height, which meets the CISPR 25 requirements. Next are the LISNs. A line impedance stabilization network is a core element of conducted emissions testing. It provides a defined impedance between the power supply and the device under test, isolates the DUT from external supply noise, and couples DUT-generated noise to a 50 ohm RF port for connection to a spectrum analyzer or measurement receiver. In this setup, I use two TechBox TBL0510-1 5 microhenry LISNs. They meet the CISPR 25 requirements for impedance, phase angle, and isolation. The number of LISNs depends on the DUT and the supply cable length. If the DUT uses a single positive supply and ground, and the supply cable is 20 cm or shorter, one LISN is sufficient. In this so-called locally grounded configuration, the DUT's ground return is directly connected to the reference ground plane. More commonly, I use a remotely grounded setup where both the positive supply and the ground return pass through separate LISNs. This dual LISN configuration allows me to separate differential and common mode noise later on, which is extremely useful for troubleshooting. I place both LISNs at least 10 cm from all edges of the reference ground plane and bond them to it using two strips of conductive copper tape. The LISNs already have grounded conductive base plates, so this bonding is not strictly required, but it fixes their position and improves measurement repeatability. The standard requires a 1 microfarad capacitor in parallel to the LISN source terminals of the positive supply line LISN. On the TBL0510-1 LISNs, this capacitor is already pre-installed by the manufacturer. On the ground return LISN, this capacitor is not required, so I remove it. In addition, I install a 1000 microfarad capacitor between the positive input terminals of the two LISNs. For the LISN used on the ground return line, I bridge the positive and ground terminals on the power supply side to tie the power supply return line to the reference ground plane. Next, I complete the power supply input section. To isolate any residual noise from my lab bench supply, I use a dedicated harness between the power supply and the LISN. This harness includes an EMC line filter and a snap-on ferrite for additional common mode suppression. I bond the line filter to the reference ground plane with copper tape, connect its output to the LISNs, and feed its input from my PeakTech 6227 power supply. CISPR 25 imposes strict requirements on the power supply. The DC output must remain within ±10% of nominal, and any RF noise from the supply must stay at least 6 dB below the applicable limit. In my setup, the filtering harness is necessary to meet these requirements down to CISPR 25 Class 3 limits. As an alternative, I can use a sealed lead-acid battery as an exceptionally clean power source. When I do that, I always include a fuse to protect the LISNs in case of an accidental short. Full compliance requires a shielded room, which this benchtop setup cannot provide. As a result, the reference ground plane is connected to earth ground with a single grounding wire instead of the multiple bonding straps required under full compliance conditions. Next, let's look at the support for the device under test and its supply lines. I use a 50 mm thick piece of polyethylene protective foam. CISPR 25 requires the DUT and the supply lines to be placed on a non-conductive support with a relative permittivity of less than or equal to 1.4, positioned 50 mm ±5 mm above the reference ground plane. A 5-volt fixed output buck converter that I recently designed serves as the device under test for the rest of the video. The positive supply line is connected to the red terminal of the positive supply LISN, with the ground return connected to the red terminal of the ground return LISN. Both the supply lines and the DUT are placed on the 50mm support. To comply with the standard, the supply lines are routed in a straight line and the DUT is positioned at least 10 cm from all edges of the reference ground plane. I use masking tape to firmly secure the supply lines and the DUT to the support. This ensures straight routing of the supply lines and consistent positioning between measurements. Next, a load simulator, using the standards terminology, is added to the setup. I use a TechBox TBOH02 self-powered active load that requires no external supply. It supports both constant current and constant resistance modes. The load is placed directly on the reference ground plane and is connected to the output of the buck converter for testing. To actually perform measurements, the LISN must be connected to the Rigol RSA 5065N, which is equipped with the EMI measurement option. I first terminate the RF output of the ground return LISN with a 50 ohm load. I then connect a BNC to N coaxial cable to the RF output of the LISN on the positive supply line. Measuring an unknown DUT can be a fast and expensive way to destroy a spectrum analyzer. To avoid that, I place a TechBox TBFL1 transient limiter in the signal path. It combines transient protection, attenuation, and a high-pass filter to protect the analyzer input. This shot of me torquing the measurement cable onto the transient limiter nicely illustrates why proper torque matters. Before this, the connection between the transient limiter, the spectrum analyzer, and the cable were only hand-tightened. Due to lever action, the analyzer side connector starts to wobble and comes loose immediately once the torque wrench breaks over. With everything in place and properly connected, it's time to measure. To set up a standard compliant measurement, I use the TechBox EMC software. After loading the appropriate segment files, CISPR 25 class 3 limit lines, and the correction files for the LISNs, transient limiter, and measurement cable, the workflow becomes largely automated. Just start the scan, let it run, and wait for the results. EMC View controls the RSA 5065N over a TCP connection and automatically applies the CISPR required resolution bandwidths and detector settings in the background. The software integrates seamlessly with many low-cost spectrum analyzers, including models you may already have. Correctly using spectrum analyzers for EMC pre-compliance testing is a topic of its own and will be covered in a separate video. While we watch part of the measurement in real time, let me take this opportunity to point out that I have linked my blog article on this test setup with more in-depth details in the video description. For a device to pass the test, it must not exceed the average limit and either the quasi-peak or peak limit on both the supply line and the ground return line. A single limit exceedance at any frequency on either line counts as a test failure. While CISPR 25 defines peak limits for pre-compliance screening, only the quasi-peak limit in conjunction with the average limit is legally binding for certification. Using the faster average and peak detectors, the full scan takes already about 8.5 minutes, so I won't show the much slower quasi-peak measurement here. And look! My buck converter passes the test, at least on the positive supply line. To repeat the required measurement on the ground return, the dummy load is moved to the positive supply LISN and the RF output of the ground return LISN is connected to the spectrum analyzer. Repeating the scan shows that the limits are not exceeded on the ground return either. Excellent. In reality, it's rare for a first revision design to pass pre-compliance on the first attempt. So let's assume it didn't and we need to dig deeper. At that point, a TechBox TBLM2 LISN mate can be added to the setup in a non-standard way to measure differential and common mode noise separately. This makes it much easier to localize the emission source and develop an effective filtering strategy. The separated measurements immediately raise suspicions about the measurements, especially above 30 MHz. The common mode noise shows no clear correlation with the differential mode noise. While that isn't strictly impossible and my design includes a fairly strong differential mode filter, it's highly unlikely. So let's take a closer look. The LISN mate is removed and the DUT is replaced by a direct connection between the LISNs and the load. In an ideal setup, there now shouldn't be any noise at all, but repeating the measurement tells a different story. The first suspicion is the power supply. I replace it with a 7 amp-hour sealed lead-acid battery and rerun the measurement. The result? Hardly any change. What the? Remember when I mentioned that CISPR 25 requires measurements in an anechoic chamber or shielded room? This is exactly why. Peaks from FM radio stations in the 88 through 108 MHz VHF band reveal how susceptible the setup is to external noise. Since the supply lines run in parallel, these external signals appear predominantly as common mode noise. How disastrous this can be to measurements is shown here. Coupling from the LED backlights on my bench, which you've seen reflected in the reference ground plane throughout the video, would completely overwhelm the measurement and violate the limits on their own. That is why performing a background measurement with the DUT removed or powered off is essential to ensure the ambient noise is at least 6 dB below any applicable limits as required by the standard. With the room lights turned off, this condition is met down to CISPR 25 Class 3 limits using either the power supply or the battery. The background scan also reveals the source of the common mode noise above 30 MHz seen earlier. Since the battery is already connected, I reconnect the buck converter and the LISN mate and measure differential and common mode noise independently. The results look very similar to those obtained with the power supply. Only a few additional peaks appear when using the power supply, which are absent in the battery-powered measurement. Using a shielded tent is an effective way to further reduce background noise while keeping the setup compact. I'll cover that approach in a future video, so subscribe if you don't want to miss it.